According to statisticians, variations in the average are more relevant than the average itself. Have you ever had the opportunity to go to a theme park where you had to stand and wait in line outside under the blistering heat? While it may seem obvious to you that if that theme park added more lines, the line would go much faster. Well, it turns out it's not that simple, and that's not actually the case. So why is that? Well, according to statisticians, and using the example of Disney and the ride Rise of the Resistance, that adding more roller coaster queues and more volume to the line won't actually reduce the length of those lineups. Right? The problem that we have is that people are showing up at different times to take the ride, and that's what causes and contributes to the lineup. In fact, statisticians are convinced of this, that Disney's hired them to tell them that adding more volume to their lines won't actually resolve the problem. It's that fluctuating demand that creates the issue. Now, Disney's come up with the Fast Pass as a way to help resolve that issue. It reduces the variance of people coming and arriving at those lines at different times, ultimately creating a better user experience. Perhaps that might have also been valuable last night if you guys were thinking about queuing theory as you're waiting to get your access point. If there had been more lines at the table, it might have been more efficient, right? It's because we all showed up at the same time. If we'd showed up distributed over an average over a 24-hour period throughout the conference, the lineup would have been much, much shorter. All right. Now, for my lengthy introduction, my name is Troy Martin, and I want to tell you about the last book that I read. All right. It's a book published by Greg Ennis called Beyond Everywhere: How Wi-Fi Became the World's Most Beloved Technology. This is a riveting tale about the histories and development of the Wi-Fi protocol. It's a real roller coaster of a ride. It's hard to put down, and I threw up random QR codes in my presentation. This particular one takes you to Amazon.ca, where you can look at purchasing the book. But the book it's a roller coaster. You can't put it down. There's highs and there's lows in the book. You're excited about the development of the protocol, and then you're caught in moments of disbelief as you hear about individuals or organizations trying to derail or delay the development of the standard. All right. There's been some talk about space and different countries and agencies that work as part of the space program. The universe is vast, right? There's a tremendous amount of size and distance. It's very difficult just to comprehend just how big it is. There's billions of galaxies, and within those galaxies, billions of stars. Right? Our Milky Way galaxy alone is 100,000 light years from one end to the other. Right? Our nearest star, Proxima Centauri, is 4.24 light years away. Our closest galaxy, the Andromeda Galaxy, is about 2.5 million light years away. There's a tremendous amount of space out in the universe. Now, if we started thinking about that space in terms of time and the distance between those celestial bodies as gaps between frames being transmitted across our airspace, we could start thinking about what would be the smallest unit of time relevant to Wi-Fi, right? In physics and chemistry, we came up with atoms, right? In Greek, the word atomos means the smallest indivisible unit of matter, right? Now, we know there's items that are smaller than atoms, but if we start thinking about that concept, what could that be? Would transmit opportunities, would they be the smallest unit that we have? What about time units? That sounds kind of convenient. In fact, 100 time units is what we've defined as a standard beacon interval. Or maybe something like time slots would be better. Now, they're not fixed in size. The time slots will vary based on the protocol and the frequency that you're using, but time slots could be a good reference. Now, all of this has been pretty abstract, so I want to dial it back into something that's a little more relevant for wireless engineers. So I was inspired by Einstein, who wasn't particularly significant. He was rather kind of a mediocre person, a mediocre violinist, didn't do well in school. No one really wanted to hire the guy, but he came out with some pretty cool ideas. right? One of them was the space-time domain, which I'm going to buy into that a little bit and modify this and have Wi-Fi people think of this as the space-airtime domain. So within that domain, if we were to look at spectrum captures, we'd have periods of transmission and then significant gaps in between those frames, right? And we can look at different perspectives on different frequencies or different places in our universe. Now, a lot of this creates a certain amount of uncertainty. We don't have the ability to predict when those frames will be transmitted, which ultimately leads us to collisions, right? So what can we do to try avoid those collisions? This brings us back to Greg Ennis's book, right? As he was developing the Wi-Fi protocol, one of the biggest challenges he had was figuring out a mechanism to avoid those collisions, right? And combating the centralized architecture versus distributed architecture within the Wi-Fi protocol. So they came out with the carrier sense multiple access collision avoidance mechanism. Now, I've drawn this as a different picture. Some of you may be used to seeing this as a workflow or a sequence or a series of steps. I drew it as bubbles, right? Because we were talking about space and celestial bodies. And in this diagram, every time a wireless radio has a frame that it wants to transmit, it's picking a random number. Once it has that random number, it needs to make sure that no one else is transmitting at the same time. And to keep everybody in sync, they'll wait gaps in time, fixed amount of spaces, and then to avoid stepping on top of each other, they count down that random number that they selected in a sequenced series of steps. And this is how we avoid colliding with other devices transmitting. Sometimes I describe Wi-Fi as a Canadian protocol. If you've ever experienced two Canadians argue, it boils down to figuring out who's going to let each other through the door first, right? No, you go first. No, you go first. It's basically a dance-off. So the problem we have in Wi-Fi is that transmitters want to avoid stepping on top of each other, and they want to let someone else jump on the dance floor first and transmit. Now, to tie this back into the relevance and more complicated scenario of voice devices communicating, if we think about a voice protocol, voice application using G711, voice frames need to be sent every 20 milliseconds, right, at those fixed intervals. And we have a high risk of devices talking on top of each other. And so if we take a look at the transmit opportunity, we have that fixed space and time, that diff interval. We have a randomized period called our contention window, our voice frame, which gets launched into the air. In this example, we're in a universe without QoS, right? So we have the benefits of being in the multiverse, one without QoS, one with QoS. We rig this game so that acknowledgements are always successful and complete that transmit opportunity. But to make it more relevant, we can throw in some time frames to this, right? Getting back to how much time slots are being consumed. And in this non-QoS voice frame that's sent, we're consuming about a planet-sized worth of 300 microseconds. Okay. Just want to take a quick detour here and give a shout out to Andrew McHale, who wasn't able to join us this week. But because I'm talking about voice, I do highly recommend checking out a whole bunch of his talks that he's given on how to troubleshoot and analyze voice networks across your environment. So harass Andrew for not being here, and maybe he can join us next year. All right, so back to the program. Talking about probability, I have a little picture of a bell to inspire you, right, about the shape of a curve. We have a normal distribution, right? We could use this to try predict what that random dice roll would be for our contention window, right? But these normalized curves, they're more useful for measuring the variance in device capabilities and how sensitive they are, right? So if you look at the iPhone 7, they don't have the same receive sensitivity. But the iPhone 15 was actually so exciting that longtime Windows proponent Raymond Hendricks actually migrated to the iOS world, right? So he's been converted because of the Wi-Fi 6E capabilities in the iPhone 7. But again, I want to make you guys feel more comfortable and less abstract, so I'm going to overlay this probability curve on a direct sequence spread spectrum curve. So in a normal curve, we have our classic bell-shaped structure. We have our means, which you can also think of as an average, which is useful for describing normal distributions, right? We have a median, which can be valuable for non-uniform distributions where you may have the interference pattern of a microwave, right? It's skewed to one side. Now, it turns out that that roll of that dice or that random number, it's neither of those. It's actually a uniform distribution, which means that there's a 1 in 16th chance that we'll always be picking one of those random numbers. Right? So it adds a little bit of the complexity here to our model that we're trying to build. Now, if we move into a QoS-based universe, right, not only do we change those fixed intervals in time, but we assign random pools of different sized numbers for each of those clients to pick. Right? Now, Wi-Fi has decided to go with 4 types of categories for differentiating different applications. Based on this picture, it makes sense that we want to pick voice to align our voice traffic for. So we're looking at spaces, always set to be 2, and we're rolling essentially a random number between 1 and 4 or 0 and 3 if you think in binary. Right? If you wanted to throw up a token packet capture chart, this is what it looks like inside the beacon, and you can see those different values. Okay? Now, if you look at the transmit opportunity, that fixed interval can vary based on the type of QoS that we're sending. The contention window for voice traffic is around it's our 4-sided dice. And then we're sending our voice data and our acknowledgement and so on. But if you look at the size of this planet or celestial body, now with QoS enabled and that shorter contention window, we're looking at airtime consumption of about 190 microseconds. Right? Now, I am using worst case scenarios, happening to roll a 3 when I pick my contention window, so it could be smaller. But again, it's a 1 in 4 chance that I roll a 3 and pick 27 microseconds for that time period. To see these two compared and contrasted against each other, our non-QoS versus our QoS world, we can see that here. But I also want to give a shout out to Gearman. Right? The values for the frames that I was showing in my slide, they come from his airtime calculator. Right? So if you hit this QR code, it'll take you directly to this link. Unfortunately, Gearman wasn't able to join us as well this year. So if you want to reach out to him on social media, engage with him, thank him for publishing and sharing this tool. It's a spreadsheet calculator that you use. He would definitely appreciate that. Right? So now that I've kind of set the stage for the modeling, right, and all the different, or some of the different components that'll go into that, what we can use to model this is it's not just a simple roll and picking a random number, right, and figuring out the curve of the probability of that. It's much more complicated. So to do this, we use things like the Markov chain model. And the Markov chain model is a process that uses a stochastic model to describe a sequence of possible events that could have the probability that changes depending on the event that you're currently in. Right? So every time you move to a different state, we have to recalculate what possible future states are as a result of where we've gone. Right? So it's a very complicated model that we use, and this is a relatively simple way of describing it. So given a state of being sunny, once you're in that state, there's a certain amount of probability that you'll move to a cloudy or rainy state. Right? And in this particular model, being in the sunny state, there's an 80% chance that we'll remain sunny. Right? But we could flip to different positions. And each time we transition to a different event, we have to recalculate the probability of what future events will be. Right? So this presents somewhat of a challenge. And if we extrapolate this out to a non-QoS model, it ends up being relatively simple to calculate. There are less variables, less factors that we have to consider. Once we enter QoS, it becomes radically more complicated. Now you introduce OFDMA, and start scheduling different frames and assigning different resource units and factoring that into the model, it becomes wildly complex. In fact, the mathematicians and the statisticians modeling this, they're not sure they can actually incorporate all the factors and contributors to developing this model. It's the same problem we have with predicting the weather, right? We can do a pretty good job in modeling what the weather patterns will look like a year from now, but it's difficult to figure out what the weather is going to be like 5 days from now. Right? So we have that ultimate challenge, which brings us back to efficiency. Right? We have the 802.11ax standard named high efficiency. So what defines that? How do we measure efficiency? Okay? I would argue that by reducing the number of transmit opportunities, we're building efficiency into the system. If we found a way to reduce the variance between frames being transmitted, that's our target for measuring whether or not we had efficiency resulting from this protocol. It is true that in certain tests, turning on AX, you may get less throughput, but the efficiency of the frames being sent and reducing that variability, making the lineup shorter, is the goal, and that's the improvement that we're going to get. Right? So as more and more devices start leveraging OFDMA as we move to Wi-Fi 7 with ultimate eyes set on technologies and protocols like Wi-Fi 10, eventually we'll get there. Right? And lastly, I just want to remind everyone that all of your Wi-Fi designs are a blend of art and science, and a significant amount of it comes from the probability of avoiding collisions to build those highly optimized networks that we're all aiming for. Thank you.